Have you ever wondered what makes things spin? From the toy cars of your childhood to the powerful engines in electric vehicles, DC motors play a crucial role. These incredible machines harness the power of electricity and magnetism to create rotational force, setting objects in motion. DC motors are everywhere in our world, quietly powering countless devices. But how do they actually work? The answer lies in a fascinating interplay of simple scientific principles. By understanding the basic components and their interactions, we can unlock the secrets behind these mechanical marvels. So, get ready to embark on an exciting journey as we delve into the captivating world of DC motors. Before we peek inside, let's start with what we see on the outside. A typical DC motor might look like a metal cylinder, sometimes with a shaft sticking out of one end. Don't let its simple appearance fool you though. That unassuming exterior houses a precisely engineered system of components working together in perfect harmony. The metal casing, often called the motor housing, isn't just for looks. It provides structural support and protection for the intricate workings inside. At the end of the shaft, you might find gears or pulleys ready to transfer the motor's rotational power to other mechanical parts. These external features hint at the hidden power within, ready to be unleashed. Now let's dive deeper and explore the fascinating components that bring a DC motor to life. At the heart of every DC motor lies the power of electricity. Just like your TV or your computer, a DC motor needs electrical energy to function. This energy typically comes from a battery or a direct current DC power supply. When we connect the motor to a power source, we create a closed loop, or circuit, for the electricity to flow. But instead of just flowing in a straight line, the electricity encounters a carefully designed obstacle course inside the motor. This obstacle course, made up of wires and magnetic components, forces the electricity to interact with magnetic fields. This interaction is what generates the rotational force, or torque, that makes the motor spin. Section 4. The Stator, a magnetic force field. Inside the motor housing we find the first key component, the stator. The stator is the stationary or non-rotating part of the motor. Its main job is to create a strong, constant magnetic field. The stator typically consists of permanent magnets or electromagnets arranged in a circular pattern. These magnets produce a magnetic field that fills the space inside the motor housing. Imagine the stator's magnetic field as invisible lines of force flowing from the north pole of the magnet to the south pole. This invisible field will play a crucial role in interacting with the electricity flowing through the motor, setting the stage for rotational motion. Section 5. The rotor spinning with purpose. Now let's meet the rotor, the rotating heart of the DC motor. Positioned within the stator's magnetic field, the rotor is a cylindrical structure mounted on the motor's shaft. Wrapped around the rotor are coils of wire called armature windings. When electricity flows through these windings, it creates its own magnetic field around the rotor. Remember the stator's magnetic field? Here's where the magic happens. The rotor's magnetic field interacts with the stator's field, causing attraction and repulsion between the magnetic poles. This interaction creates a twisting force or torque on the rotor, making it spin on its axis. The direction of this spin depends on the direction of the current flow and the orientation of the magnetic fields. Section 6. Commutators and Brushes. Keeping the current flowing. As the rotor spins, we encounter a challenge: how to maintain a continuous flow of electricity to the rotating armature windings. That's where the commutator and brushes come in. The commutator is a split ring mounted on the rotor's shaft. Each segment of the commutator is connected to one end of the armature windings. Stationary brushes, typically made of carbon or metal, make contact with the commutator segments. As the rotor spins, the commutator segments slide past the brushes, constantly changing the path of the electrical current flowing through the armature windings. This clever arrangement ensures that the current always flows in a way that keeps the rotor spinning in the same direction. The commutator and brushes work together as a switching mechanism, reversing the current direction in the armature windings at just the right moment to keep the motor running smoothly.